time we had one of these class meetings, we've covered a lot of new material in the lectures. I want to just do a bunch of these new kinds of problems. First, I want to make sure that everybody's finding the assignments and the lectures and stuff. I did just check the first, who turned in the first assignment. And there are still a few people who haven't turned anything in. So I just want to make sure if you haven't turned it in, like we're on the same page about where to find the lectures, where to find the notes, where to find the assignments. Anybody have any questions about that? Yes.
Are your daily assignments going to be
doing? I'm switching to one Tuesday and one Friday. Yep. Up until now, it seems to have been Tuesdays, but I need to switch to 2 a week.
Okay.
And then there were a couple of people who turned in assignments that didn't show the steps. You need to show the steps of what you're doing. You can't just show the answers. That's just a habit you need to get into for physics in general. Show the equations you're using. For unit conversion, you need to show your units all the way through. If anybody who turned something in that didn't have that stuff, I put a note in the grade book in D2L. So look for that if you didn't get a 1 out of 1 on the first assignment. Okay, next. Anybody have any specific homework problems that you'd like me to do? I'd be happy to work through any that you'd like. Sometimes it helps to see someone do it while talking through it and stuff instead of just looking at the solution. Otherwise, if no one has any specific questions, I'm going to just go through some sort of similar examples, but different problems. Nothing? Okay. Well, in the last week of lectures, you saw videos on the definition of position and position versus time graphs, and then the definitions of velocity and acceleration. And there were really 2 main kinds of problems that you saw examples of and that have been assigned so far. So let me just do some of those. The first kind is, it just describes a motion. It's like this object goes from here to here to here to here, and it takes this long for each step. If you choose your 0 position to be at the tree and your positive direction to be toward the fish, draw a position versus time graph of the motion. So let me do a couple of things like that. I guess I really just have one example like that, but we'll do it with a few combinations of positive direction and 0 position. And okay, so this is like an illustration of what the morning is like for me every single day. So here's the kitchen. What do you have in a kitchen? A table with an apple. And then here's a chair. And then here's my car. And let's say that it's from the kitchen to the chair is a distance of 10 meters. And from the chair to the car is 30 meters. And so let's say I go from the kitchen to the chair in 10 seconds, but then I forgot my breakfast on the counter. So then back to the kitchen in 10 more seconds. Then back to the chair in 20 more seconds. It's slower because I'm getting demoralized. And then it's time to go to work. So from the chair to the car in 20, I need more time than that, 40 seconds. And then I forgot my bag. So back to the chair. In 40 seconds. And then back to the car in 50 seconds. Okay, so that's the whole motion. And we want to draw a position versus time graph of this. Before we can do that, we have to choose an instant that's going to represent our 0 time. So let's say 0 time is, when I start in the kitchen. The 0 position we'll start with it in the kitchen. Okay. And the positive direction will be from the kitchen, toward the chair and the car. Those two are all in one direction. My house is just one long line. Not really, but. So let's say toward the car. Okay. Okay, so how are we going to go about doing this? So our choices of the 0 time and the 0 position and the positive direction, those are going to change the numerical locations of these things and the numerical times of these instants. So what I'm going to do is I'm going to first draw out just a little diagram of what's going on, okay? So here's the kitchen, the chair, and the car. Okay. And what you choose is your 0 position, positive direction, 0 time. Those don't affect the actual motions that happen. So in all cases, I'm just going to draw, sketch out an illustration of the motion. It doesn't have any numbers associated with it yet, but it's going to start in the kitchen, go to the chair, go back to the kitchen, go back to the chair, okay, then out to the car, back to the chair, and then finally back to the car. Okay, so that's the motion that's happening no matter what you call your zeros and stuff, okay? Not having a physicist watching you doesn't change whether you can go places, but it is going to change the numerical values that we associate with the times and positions, okay? So now for the first, let me actually save this because this is the stuff that's going to be the same for every choice, set of choices we make of 0 time, 0 position and stuff. This stuff is not going to change. Now that we have this motion labeled, now we can go through and put numerical positions on the different locations and assign numerical times to the different instants that are happening. So it says 0 time is when you start in the kitchen. So that means that this instant here is at 0 time. From 0 time, it takes 10 seconds to get to the chair. So if it takes 10 seconds and you start at 0, so say that 0 time is when you turn on a stopwatch. What would the stopwatch say when you first get to the chair here? 10, yep. It takes another 10 seconds to get back to the kitchen. So what would it say at this instant? 20. Then it takes 20 seconds to get back to the chair. So what would this one say? 40. Then it takes 40 seconds to get to the car. So what would this instant say? 80. And 40 to get back, so 120. And then what did I say, 50? So 170 seconds for this instant. So those are, if you start your stopwatch when you start walking in the kitchen, this is what your stopwatch says at all those instants, okay? And now we can label all the locations numerically because we know that we're choosing, you know, it says our 0 position is going to be at the kitchen. So that's our 0. And our positive direction is this way. Okay, those are the things that are given. We know the distances between these things, 10 meters and 30 meters. And now that we know the 0 position and the positive direction, now we can assign those locations numbers. So if this is 0 and you go 10 meters in the positive direction from 0, what's the numerical label for the chair? Yep, this is 10 meters. And if you go another 30 meters in the positive direction from 10, what's the numerical label for the car? 40, yep. And so now to graph this out, we can, you know, write out like a little table of, you know, the times and the corresponding positions. So what we, like really what we want to do is just, in this table, put down the positions and times at each one of these points that are, you know, each one of those dots. So at the first instant, we're at 0 time and 0 position. That doesn't always have to be the case. We'll do an example of this where you don't start at 0 time or 0 position, but that's what it has to be in this case. At instant 2, the time is 10 seconds. And what's the position? Ten, yep. Anybody have any questions about that? On some of these early things, it can be like, it can be hard to tell like when people are confused and when people are bored, and sometimes you're a little confused and a little bored, but try to let me know if you, because it's a lot easier to do this stuff if you straighten out the confusion early, you know. Okay, so the third instant is back in the kitchen. So what's the time there?
20.
20, yep. And what's the position? 0, yep. And then the next one is here. So what's the time? 40. And what's the position? 10. And then the next one is here. What's the time? 80. And what's the position? 40, good. 40 meters. And then this graph has a lot of points on it. And then 120 is the next time. And what's the position for that? 10. And then the last one is 170. And the position is back at 40 meters. So a position versus time graph. Position is always going to go on the y-axis. Time is always on the x-axis. So let's see. I'm just going to write out the numbers that occur here. So the x-axis is the 0 for position. Then we have 10 and 40. So 10 meters and 40 meters. And then for times, we have 0, 10, 20, 40, 80, 120. Okay, so 0, 10, 20, and then 40, 80, 120. Oh, and there's still a 170 way out there. $80. 120. 170. And now that we've done all this like setup work, all we're doing is plotting those points. So, you know, each one of these pairs is a coordinate pair, and you're just plotting it. So 0, 0, 10, 10, 20, 0, 40, 10, 80, 40, 120, 10, and 170, 40. And you can connect those as straight lines or curved lines. That doesn't really matter for this exercise. But that's what a position versus time graph looks like. Anybody have any questions about that? Okay, let's do another one, and we'll change all these. So we'll change what we're calling the 0 time, the 0 position, and the positive direction. Okay, and we'll see how that affects things. It doesn't affect the motion. The motion still starts in the kitchen and blah, 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 but it changes the numerical locations, the numerical labels of these things. Okay, so for part B, let's say 0 time is 20 seconds before you start in the kitchen. So like, that's like if you start the stopwatch, you think something's going to happen, but it doesn't for 20 seconds. And when something starts, your stopwatch says 20 seconds. Okay. 0 position, let's say, is at the chair. And the positive direction is toward the kitchen. Okay, so let's see what these choices change. Okay, so here's the motion. I just copied that from before because the motion doesn't change, but our labels are going to change. Okay, so with this choice of 0 time, let's label the times on these instants. What's the time when the person starts walking in the kitchen? 20. So 10 more seconds is 30. 10 more, yikes. 10 more seconds after 30 is 40. How long does the next one take? 20. So then this is 60. And then it takes 40 to get to the next point. So 60 plus 40 is 100. 40 more is 140. And 50 more is 190. So that's all the time labels. Now the position labels, 0 position is at the chair. So put the 0 there. And this time the positive direction is from the chair toward the kitchen. So positive is this way. Okay, that doesn't change anything about the distances. But if you start at 0 and go 10 meters in the positive direction, what's the label in the kitchen now? So start at 0, go 10 meters in the positive direction. That's positive 10. And if you start at 0, you know, the opposite of the positive direction has to be the negative direction. So if you start at 0 and go 30 meters, is that what it was? Yeah. Go 30 meters in the negative direction, what's the label at the car now? Negative 30, okay? And so now we can start to fill out this this table of the values. Okay, so at the first instant, we have a time of 20 seconds and a position of 10, right? Position of 10 meters. At the second instant, we have a time of 30 seconds and a position of 0. Yeah. Okay. So the so this motion is still the same, right? Like it doesn't change what the person does. The only thing that changed is now we're saying the chair is 0 and positive is from the chair toward the kitchen. So the person still starts in the kitchen. It's just now the kitchen is positive 10. Okay. And they still go to the chair next. It's just that now we're calling the chair position 0. Okay. So 30 seconds, we're at position 0. At 40 seconds, we're back at position 10. At 60 seconds, we're back at position 0. At 100 seconds, we're at position negative 30. At 140 seconds, we're at position 0. And then the last one at 190 seconds, we're back at position negative 130. Okay. All right, so this time, we're still going to just plot out these pairs. Our position is always going to be y, and our time is always going to be on the x-axis. But now we have, we have to plot a different range of values. On the position now, we're going to have 0, positive 10, and negative 30. And for time, we're going to have 20, 30, 40, 60, 100, 140, 190. So this is 20 seconds, 30 seconds, 40 seconds, 60, 100, 140, and 190. And now just plot these coordinate pairs. 20 seconds, 10 meters. 30 seconds, 0 meters. 40 seconds, 10 meters. 60 seconds, 0. 100 seconds, negative 30. 140, 0. And 190, negative 30. And if you plot these, it looks like that. And if you want to understand the relationship between these, it's not really important that you do. I mean, the main thing is just understanding how your choices of 0 time, 0 position, positive direction are going to affect all these values, But notice that the shapes of these two things, there's something that's the same about the shapes. They're shifted, one's shifted upside down because we changed the positive direction. If you switch the positive direction, it flips things upside down. It's shifted to the right because we changed the 0 time, and it's shifted up or down because we changed the 0 position. So that's what the shifts are that's happening, but that's really not the key thing you have to remember about this. Anybody have any questions or any frustrations to vent about this problem? Okay, good. So in the assignments, I make you do a few problems like this. I think it's really useful before you start doing kinematics problems, constant acceleration problems. And hopefully once this stuff makes sense, it'll make sense when you put it in the kinematics equations. Okay, so after we talked about this kind of stuff, and this had to do with the definition of position, and then kind of with velocity and acceleration, although we really aren't talking about that here. The next thing that the lectures talked about was the constant acceleration equations. And the three constant acceleration equations said P final is equal to P initial plus V initial times time final plus 1/2 times A times T final squared. And the second one said V final is equal to V initial plus A times time final. And the third one said 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And the meanings of the subscripts are P initial and V initial are the position and velocity when time is equal to 0. Position final and velocity final mean the position and velocity when time equals time final. And then the acceleration is constant, so that's the same no matter which one you're talking about. And in the lectures, I gave you some steps to follow. I think at the start, I would just follow these steps, just have the steps in front of you, and just follow them, make sure you're not missing anything. Eventually, you'll do a few of these problems and it'll start to get just sort of natural. And then you don't have to be quite as careful. You'll sort of just follow the steps naturally. But the steps are first, you have to choose 4 things. And this is very closely related to these kind of problems, okay? Where you're choosing a 0 position, a positive direction, a time equals 0. In these problems, you also have to choose sort of a final time, your time T final, but that's the only thing that's different. So you have to choose 4 things. An instant corresponding to time equals 0. An instant corresponding to time final. A location corresponding to the position equals 0. And a positive direction. You can think of the times as being turning on and turning off the stopwatch. And you can think of the position and positive direction as kind of like laying out your tape measure. What direction are you laying it out? And where are you putting the 0 of your tape measure? That's where all the measurements are going to be taken from. Okay. Once you've chosen those 4 things, you have to figure out what you know and what you want. And you can just go through all of these equations. There's only, I think it's only 5 total variables. Let's see. T final, acceleration, P initial and P final, V initial and V final, so 6. Okay, there's 6 total variables, and you just go through the list and ask yourself, which ones do I know, which ones am I asked to find? So the variables are t final, acceleration, p initial, p final, v initial, v final. You can just go through the list. Third, you have to try to find one of those constant acceleration equations that, so find an equation. It has to have, so that has the variable you're looking for, the variable you want. And every other variable in the equation is known. In order to use one of these equations, this has to be satisfied because with one equation, you can only solve for one variable, you know? So if you have 2 variables in your equation, you can't do anything with it. Sometimes in problems later on that we'll get to, none of those 3 equations work, okay? If that happens, what you have to do is solve for an intermediate variable and then go back to step 3, basically. So you have to solve for some variable that you didn't know before. And that's almost always going to be t final or acceleration. And just go back to step 3. Okay, so I just have a few example problems to do. I'm going to do some by myself, and then I'll give you a chance to do some related to these two, just to make sure that this is all making sense. Okay, the first one, let's say that a boat is at rest at the dock. And let's say from rest, it takes 45 seconds to get up to a speed of 20 meters per second. You want to know what's the acceleration? And how far has the boat traveled when it gets up to 20 meters per second? So let's just go through the steps. The first step, We have to choose those 4 things. Our time equals 0. So actually, generally, to choose your time equals 0 and your time final, you're trying to choose instance where you either are given information or you're trying to find information, because those instance time equals 0 and time final are the only places that you have any variables. So they're the only places where you can solve stuff or put values into the equation. Okay, so in this case, the instant where we know stuff and the instant where we're trying to find stuff are when the boat is at rest and it just starts its acceleration, and when it reaches 20 meters per second. So those have to be our time equals 0 and time final. There's no other choices. Any questions about that? So our time equals 0 instant is when it starts the acceleration. The time final instant is when it reaches 20 meters per second. Our position, so this is sort of interesting. These 2 things, you have to get those right. There aren't really any, there's no wiggle room on those. If you don't choose those right, you can't do the problem. For the position equals 0 and positive direction, those are really just, you can do this problem no matter what your choice of those are. All those can do is make the math a little simpler or a little more complicated. But you do have to be consistent with them. So we still have to be clear to ourselves about what we're using. So our position equals 0. Let's say that that's at the dock, or that's at the boat's location when it starts the acceleration. I'm going to write that as the boat's location at time equals 0. Okay. And whenever you choose your position equals 0 to be the object's location at time equals 0, that, if you think about the definition of initial position, that makes your initial position 0. So it can sometimes sort of simplify things. So this tells us that P initial is going to be equal to 0. And then our positive direction, well, this boat, we're treating it like it's going in a line. Let's just say the positive direction is the direction of motion. You could do it opposite the direction of motion, and you'd get the same answer, but I'm going to choose positive direction is in the direction of motion. Okay, so next we have to think about what variables we know and what variables we want. I'm going to list out these 6 variables, and we can just go through and cross them off our list as we think about each one. Over here are going to be the variables we know values for. Over here, there's going to be, I'm just doing part A to start with, so there's just going to be one thing that we're looking for. Okay, so we know that time equals 0 is when the acceleration starts. We know time final is when it reaches 20 meters per second. Do we know the number of seconds that it takes between those two? Is that something that's given in this problem? 45 seconds, yep. So time final is 45 seconds. Do we know the acceleration? Do we want it? Yep, that's the thing we're asked for, so I'll put that over here. So we know our equation has to have A in it. All 3 of these equations have A in it, so that doesn't help us narrow it down. Do we know initial position? So do we know the position when time is equal to 0? Yes, because of our choice of the 0 position, this is equal to 0. Do we know P final? No, we don't know that. We're going to try to find that for part B, but for now, I'll just leave that blank. Do we know the initial velocity? 0. It's at rest at time equals 0, so VI is equal to 0. And do we know V final? There's sort of two things to think about here. Yeah, so we know that the speed is 20 meters per second, and then we have to think about the direction it's moving to. And that has to do with what we chose for our positive direction. We chose our positive direction to be in the direction of motion. So our velocity is going to be 20 meters per second in the positive direction. So that's going to be positive 20. If we had chosen our positive direction the other way, that would have been negative 20. So when you're thinking about velocities, sort of think of the speed and then think, is it going in the positive or negative direction? Okay. So I'm going to write this as positive 20 just to be like emphasize that the direction that the thing is moving determines the sign of the velocity. Okay. All right, so we're looking for A, and we know these 4 variables. What we want is to find one of these 3 constant acceleration equations where A is in it. That doesn't narrow it down at all. And then everything else that's in it is in our column of stuff we know. Okay. So what works here? You can just try one equation after the other and just look through, you know. We know time final, P initial, V final. So we could use either one of these 2 equations. We could use the first one of these or the second one of these. If you have a choice between the first and second, might as well always choose the second because it's a little simpler and you never have to worry about a square. But either one would work. So I'm going to use V final is equal to V initial plus A T final. So plug these values in, you get 20 meters per second is equal to 0 plus A times 45 seconds. And now you can, for now, I want you to keep track of your units as you do these calculations. Later on, you won't have to do that, but I want you to see how this works. If you're careful with your units in all these calculations, the units on your answer will come out correct. So I'm going to write this as 20 meters over seconds. Okay. We're going to divide both sides by 45 seconds. And that's equal to the acceleration. And look at the units that come out, meters per second squared. Those are the units of acceleration. So acceleration comes out to be 4/9 meters per second squared. From what you know about acceleration, so remember in the, well, let me write this again. So in one of the lectures, it said that if an object is speeding up, velocity and acceleration have the same signs. If an object is slowing down, then velocity and acceleration have opposite signs. So does it make sense in this case that our acceleration is positive? Yeah, because our velocity, where was that? If you look at our list of what we know, and our velocity was positive. This boat is speeding up, going from rest to some higher speed. And so we know the acceleration should be positive, and that's what happened. If we had chosen our positive direction the other way, and our velocity would have been negative, we would have gone through all this calculation and gotten the acceleration of negative 4/9 meters per second squared, which physically would have meant the same thing. The acceleration was still in the negative direction, in the same direction as the velocity, and so it was speeding up. Any questions about that first part? So now the last thing we want to figure out is how far the boat went during that time that it was accelerating. So let's just think about the steps again. The first step is making those 4 choices. Time equals 0, time final, position equals 0, positive direction. Can you think of any reason in this problem that we need to change any of those? Normally, the only reason that you would have to change those is if you're trying to calculate something at a different instant than in the first part of the problem. And in this case, we're not, right? We're trying to calculate the position at one of our old instants. You see what I'm saying? And so we're just going to keep the same things. So all these 4 choices are going to stay the same. And if all of those 4 things stay the same, then everything we knew before, we still know. And whatever we calculated before, we know now. So if we list out the things we know and what we want, we can just go right back to all the stuff we knew before. And now we can also include the thing that we calculated. What's 4/9? Is that 0.44444? I think it is. I'm going to just write it as a decimal. Our initial position was 0. Do we know our final position? No. Do we want it? That's what we're trying to find. Yep, so that goes over here. Our initial velocity was 0. Our final velocity was, what was that, 20? Yeah. Okay, so what equation works for this? I think we could use the first equation or the third equation. I'm going to use this one, the first one, that says P final is equal to P initial plus V initial times time final plus 1/2 A T final squared. And let's just plug the values in. So P final, what we're looking for, is equal to 0 plus 0 times something is 0 plus 1/2 times 0.444 times 45 seconds squared. Oh, I didn't put the units in. Remember to put the units in here. So 45 meters per sec, 0.444 meters per second squared times 45 seconds squared. And so what does this mean if we keep track of all those units? So P final is equal to 1/2 times 0.444. I'm going to start out by combining those two, and we get 0.222 meters over seconds times seconds times 45 seconds times 45 seconds. You can see that this second cancels that one, this second cancels that one, and the units we're left with are meters, which is what we expect for position. And can someone multiply this out? 0.222 times 45 times 45. $449. Okay, 0.55, and that's meters. And that answer is positive, so this says that the boat has gone 449.55 meters in the positive direction since it started. And it makes sense that it went in the positive direction because positive we chose as the direction of motion. Any questions about that one? Yeah.
Wouldn't it actually be 450 if we used it as 4/9 instead of 0.444?
4/9. Oh yeah, that would cancel one of the 45s. Yeah, you're probably right. You're probably right, but I don't care about that. But yes, I bet you're exactly right. I make all my decisions about rounding based on how angry I can make the chemistry people. Any other questions? All right, let's do one more. And this one, I'm going to do one that's like related to the lab we did last week. So let's say that you did your 30 measurements of how long it takes for an object to fall 2 meters. Okay, so this pinball was dropped a distance of 2 meters. And the average time that it took for it to hit the ground was 0.64 seconds. So if we assume that gravity is accelerating this, is that this ball in free fall is in a constant acceleration. So if the acceleration of gravity is constant, what's the acceleration of gravity from that experiment? So that's if we did this measurement right, it should be 9.8 or between 9.80 and 9.81. I usually use 9.81, but yeah. And I did, that time I chose is pretty close to, is going to give us an answer that's pretty close to that. So let's see how we would calculate that. Because we did the experiment, measured all the times, did all the stuff, but we didn't take the step of seeing what that told us about the acceleration of gravity. But that's what you could use this experiment for, is to see how quickly, how much gravity accelerates an object that's in free fall. Okay, so let's just go through the steps. So first, we have to choose a time equals 0 instant, a time final instant, a position equals 0, and a positive direction. And like I said last time, those 2 times, we have to get those right. The other 2 are just, is really just relative. We can do everything no matter how we choose those. But so what do you think we're going to choose as our 2 instants? There's sort of 2 instants that stick out where we have information and or want information. One is the instant where we drop the ball. What do we know at the instant we drop the ball? Really 2 things. One is said explicitly. We are not leaving till you answer. No.
0.64 seconds to hit the ground.
That's 0.64 seconds is going to be our time final. Okay. So we know that. What do we know, like right at the velocity is 0. Yep, it's not moving. And then we know it's 2 meters above the ground. Yep. So time equals 0 is going to be the instant that it's released. Time final is going to be the instant that it hits the ground. Okay, now these are the 2 where we could choose anything we want and get these answers right. On free fall problems, I tend to choose position equals 0 to be the lowest point in the problem, so I'm going to put it on the ground, but you don't have to do that, you know. In fact, if you're interested and have extra time, you know, try this problem later with a different choice of 0 position. Try it where it's dropped from, and try the positive direction the other way. And you'll see how you end up with some numbers that are different, but if you interpret them physically, you realize like, oh, it's giving the same answer, you know. So position equals 0 is the ground. And positive direction, I'm going to choose up. And then second, list out what we know and what we want. So here are all the variables. It's the same 6 variables for every one of these 1D problems. T final. Okay, do we know the seconds value for T final?
0.64.
Yep, that's right. So TF is equal to 0.64. A is what we're trying to find. Do we know the initial position?
0.
It's positive 2. Yeah, just because I chose 0 to be on the ground and positive up. So if you start at 0 and go 2 meters up, you're at plus 2. So P initial is positive 2 meters. Do we know final position? 0, yep. Do we know initial velocity? Someone already said this. 0, yep. And do we know final velocity? No. It's going to be, okay, so that actually brings up an interesting point that you have to be careful with, and I'll bring this up later, but since it's brought up here, this object is only in constant acceleration until it hits the ground. So we can't consider the instant when it hits the ground. So really the end of our problem isn't when it hits the ground exactly, it's like the instant before it hits the ground. And so we don't know what the final velocity is. It's going fast, you know, it has some speed going down. One thing, just as an exercise, what's the sign of the final velocity? This is a good thing to make sense out of. Negative, yes, because we chose our positive to be up. The object is moving down, so its velocity has to be negative. And if we took another step at the end and calculated its final velocity, we would see that. Okay, so here's what we know and want. Are there any of those three equations that have acceleration in it and everything else in it is known? The first one again, yep. So P final is equal to P initial plus V initial time final plus 1/2 A time final squared. So start filling these in. 0 is equal to 2 meters plus V initial is 0, so the second term is 0, plus 1/2 times A times 0.64 seconds squared. Okay, so subtract 2 meters from both sides, so we have negative 2 meters. And then I'm going to multiply both sides by 2 to get rid of that 1/2. And then I'm going to divide both sides by 0.64 seconds squared. So divide once, 0.64 seconds, and divide again, 0.64 seconds. And all this is equal to the acceleration. I sort of did that all in one step, but you could do it in 3 lines. You know, first multiply by 2, you get your expression. Now divide by 0.64 seconds, you get your expression. Divide by and it's a little more obvious if you break it up into steps. Anyone have any questions though about what I'm doing here? Okay, so what do we get? We know we have units of meters per second squared, which is good because that's units of acceleration. Can someone multiply and divide out these numbers?
Negative 9.77.
Okay, negative 9.77 meters per second squared, which is pretty close to the true value of 9.81, but there's some error in the experiment or whatever. And my last question is, so this is something you should always ask yourself when you get an answer, like, is there anything about that answer that I can tell is right or wrong? Is there anything I can use to sort of troubleshoot? What about this negative? Does it make sense that the acceleration is negative? There are 2 ways you can think about that. One is gravity accelerates things down and our positive direction was up, so negative is down, so that's good. And then the other one is, as this thing's falling, it's speeding up, right? we said our velocity was going to be negative. So speeding up means acceleration also has to be negative, and so that checks out. So we don't have a way to really know by thinking about it whether that number is right, but we can see that the units came out right, and that gives us confidence, and we saw that the sign came out right, and that gave us confidence. Any questions? Okay, so that's it. I will give you another assignment tomorrow, and I think the next one is about free fall. So you'll just get more information about problems like this. And keep emailing me if you want to meet over Zoom. And Friday mornings I have office hours in the tutoring center. All right, see ya.